Hello, everybody, and welcome to Explaining Exoplanets, sponsored by Thallimer Observatory. My name is Todd Thallimer, and I am the primary amateur astronomer at the Thallimer Observatory. And today, we are going to try and broadcast live here on YouTube. We don't have a great upload internet speed because we're out in a rural area, and so there's not a lot of internet options. So uploading is sometimes a little tricky, but hopefully it's coming through okay. So we are going to, and I believe we have a live chat available here on YouTube as well. So we'll give that a try, and I'll check on that from time to time, see if there's any questions as we go along. And I think that's it. I think we're going to get started. Today we're talking about exoplanets. About how we detect them, what they are, how many of them there are, life on other planets, all that stuff. So that is where we are. And yeah, I think we'll go ahead and get started. Okay. So a little bit about me first. Like I said, my name is Todd Thallimer, and I'm an amateur astronomer. I have a domed observatory in Elizabeth, Colorado, and I like to do outreach with the public. And so this is, of course, one of those events, and this will be archived on YouTube so that we can, if you weren't able to watch it live, it will be available at another time that is more convenient to you. So here on the slide, you can see a picture of my observatory, and there I am up on the deck giving a talk. This is Astronomy Day in 2015, and I was giving a talk about the birth, life, and death of stars. Really popular event in the local community. Had about 100 people there out on my lawn coming to hear the talk, and then afterwards we looked at some things through the telescope that we talked about in the talk. So we're not really doing talks at the observatory anymore, just because it's our own private yard, and it's kind of strange that we have a lot of people we don't know in our own yard. So we are doing some outreach at different places around the Denver area. Definitely find us on Facebook, Thallimer. Yeah, just search for Thallimer Observatory on Facebook. It's the easiest way to find out where we are and the events that we have coming up. You can see pictures that we've taken in the observatory. Sometimes we broadcast live from inside the observatory as well. So a lot of fun stuff on our Facebook page. We have a couple hundred people that follow us, and yeah, it's really exciting, especially with the upcoming eclipse this year in 2017. We're getting a lot of stuff going on. And then, of course, one of the biggest questions that we get is, what does it look like inside the observatory? Well, we have that. There's a picture of one of our small refractors mounted on our pier there in the observatory. And yeah, of course, we have all the fancy red lights and all that fun stuff as well. So this is the picture that we have here is actually our astrophotography setup for doing some wide field photography. Things like the Horsehead Nebula that we had prior to the show, and a lot of other really neat stuff we shoot with that. So that's a little bit about me and the observatory. Definitely find us on Facebook and follow us. We do work with homeschoolers and other kind of social groups like Boy Scouts and Girl Scouts, and helping people get service badges and things like that. So we go to schools and talk at schools and bring our telescope to schools. We're available for parties and all that fun stuff. So contact us via Facebook to find out more. Okay, here we go into all about exoplanets. So we're going to start off with a definition of what an exoplanet is, because that would probably be helpful. So an exoplanet is a planet that orbits a star other than our sun. So anything not in our own solar system would be considered an exoplanet. Pretty simple, basic, to the point planet that orbits another star. So why are we so excited about exoplanets? Why am I giving this talk? So exoplanets are really neat in the fact that they, of course, are not a part of our own solar system, but we have figured out that there are planets that orbit other stars. And so the main drive for exoplanets is to not only kind of discover the science around things that are like us out in the universe, but to maybe find other intelligent life, and so just a lot of scientific research about understanding more about why we're here, and of course the big question about, is there life? And I had a poll that and I'm not sure how to do it. This is a new setup for us, so let's see if I can put the poll up here. Let's see. So if I click on this, does it bring up a poll for us? No, I'm not sure how to use these cards. So, okay, we will move on since I don't know how that works. We'll try it off at another time. Basically, the poll was asking, do you believe that there's intelligent life in the universe? So that's kind of a question we want to ask several times through the talk, because it's a very interesting, an interesting idea. And I think that as we go through the presentation, your attitude might change to that question. So keep that in mind. Okay, so that's why we're excited about exoplanets. And I did this presentation originally last fall in 2016, and it was just after the Centauri Proxima b exoplanet was found. And so that was one of the big drives about why we are so excited about exoplanets. And we will talk about this in a little bit, more towards the end of the presentation, about that particular one, and about TRAPPIST-1 as well, because that was a very recent thing that came out in the news, and we'll talk a little bit about that. Okay, so there are several types of exoplanets, and we found this out through discovering lots of exoplanets. And so we began with classifying exoplanets as we began to learn a lot more about our place in the universe. And we use our solar system as an analog, the baseline of what we understand when we talk about a lot of these things. So this is one of the reasons why Pluto became a dwarf planet, because as we start understanding and have a lot more data about what's out there, we have to start categorizing it, because we can't just call everything a planet. We want to have a more defined definition of that. So that's kind of some of the background about why Pluto became a dwarf planet. And there's other dwarf planets in our solar system, but this was kind of one of the drivers that isn't talked about a lot. So several different types of exoplanets we've discovered. The first was a hot Jupiter, and that's a big planet like Jupiter that is close to its host star, which is why it's called hot. So big, close to its host star. The next one that we have would be called a hot Neptune. So Neptune's not as big as Jupiter, but it's pretty big. And usually a hot Neptune is within 1 astronomical unit of its host star. And an astronomical unit, if you don't recall from schooling, is the distance between the sun and the earth. We call that an astronomical unit. So again, going back to using our own solar system as the analog for what we understand, this is a measurement of, we know that life exists on Earth because we are here, and we are 1 astronomical unit away from our host star. So we're going to use that distance measurement a little bit as we go through the presentation. So hot Neptune, pretty big, within 1 astronomical unit of its host star. The next one would be a mini Neptune or small Earth. So that would be something that is possibly up to 10 Earth masses, which would be a pretty big planet. And notice we're not talking yet about gas planets versus rocky planets, and that's for a reason, and we may get into that in a little bit. And the last type, and the type that we are most interested in, is stuff that's like us, Earth-sized and smaller planets. We know that life exists on a planet the size of Earth. We know how far away from the sun we are. We know that we have water on our planet. So these are the ones that we are the most interested in because we know that life can happen on that size planet. So those are the several types of exoplanets. And what we've learned through the survey of looking out into the universe, or into the Milky Way galaxy, is that on average, there's at least one exoplanet per star. And from what we've discovered, there's usually more than one exoplanet around each star. So as you look up in the sky at night and you see stars, you're probably looking at exoplanets. And that's because there are so many stars out there. And what we've been able to determine so far is that there's at least one. And of course, if you go into it a little bit further, there's binary star systems, and they can also contain exoplanets, and it gets to be pretty confusing, but we're going to try and keep it really nice and simple here on the discussion. Okay, let's see. Next. So as of March 1st, 2017, we're recording this on the 25th of March, 2017, so about 3 weeks ago, there was 3,586 confirmed exoplanets in 2,691 different systems. Okay, and a system being a star system, so just like our own solar system. So you can pretty much say 2,691 stars. So you can definitely tell that there's at least one planet around each of those, because 3,586 is more than 2,691. And 603 of those are multiple planetary systems. I should have read the rest of the sentence there. So yeah, that's pretty amazing. So that's quite a lot, and we'll talk about how those were discovered and by what methods and by what machinery. And okay, 20% of those are sun-like stars. So 20% of those 2,691 are stars like our own, and they have an Earth-sized planet in the habitable zone. So that's pretty amazing discovery. And a lot of this discovery was done just in the last 20 years. So we've come a long way with that. Now there's something called the Drake equation. And don't let this formula scare you. We're not going to get too in depth about it. But the Drake equation, prior to being able to obtain scientific evidence of exoplanets, was a method that we used to determine how many planets we thought could have intelligent life on them, or be in the habitable zone at least. So the pieces of this equation, they deal with things like how far the planet may be away from its star, how many planets may be in a system, how many systems we think there might be, a lot of different factors. And the Drake equation has actually come into a little bit of, we're not using it as much as we used to, because now we're getting scientific data and we don't really need to use this equation, other than now we know a little more definite numbers that we can plug in here and not just randomly say, if there's this many systems. So now we're kind of getting a better idea of how many systems and how many planets are around each star. And so it's making this a little better. And we're going to talk about that in a few minutes, about why that has changed. There's some other factors as well that have led to the Drake equation not being used as much as it used to be. Okay. Let's see. So in our own galaxy, the Milky Way galaxy, we have pretty much figured out that there's about 200 billion stars. That's a lot of stars. And that equates, if you use some of the numbers that we used previously, that there's probably 11 billion habitable Earth-sized planets. So that would be planets the size of Earth or close to it, orbiting around a star that is just like our star at a distance where water could be on the surface. So 11 billion possibilities just in our own galaxy. So this would be a place where I would bring up that question again about whether you think there's intelligent life or not. And so now we've kind of upped the stakes here. So 11 billion just in our own galaxy, if we were able to extrapolate the numbers based on what we've found so far. So that's pretty amazing. And we've barely done surveying. Of course, we talked about, we've only had 3,586 confirmed exoplanets. There's also, I want to say there's another 4,000 or so that are unconfirmed at this time. They've been extrapolated, and we'll talk about that in a little bit about how we do that. So that's pretty amazing. All right, so let's talk about something called the Circumstellar Habitable Zone, the CHZ. Now, this is possibly a kind of a strange term, but it is something you probably have heard of. Okay, it's also called the Goldilocks zone. And if we go back to the story of Goldilocks and the three bears, Goldilocks goes through the bear's cabin and finds things that are too big, too small, just right, too hot, too cold, just right, etc. Okay, that's why we call this the Goldilocks zone. It's a special area near a star where we know if that planet is orbiting, where the surface of the planet could support liquid water if it has the right type of atmospheric pressure. Of course, if you don't have an atmosphere that's giving you pressure, all that water is just going to float off into space, vaporize. So atmospheric pressure is very important. Liquid water is very important. And the distance from its given star is important. And that would be the Goldilocks zone. We don't want those things too close, or else they burn up. They burn the atmosphere off. Anything on the surface may be irradiated. If it's too far, it freezes. As we've seen in our own solar system, we've seen some of these things. So Goldilocks zone, also called, so the Circumstellar Habitable Zone is also called the Goldilocks zone. There's also another name for it, but I can't recall. So this is determined by the star type and a few other characteristics where that Goldilocks zone may occur. Now, we know in our own solar system that we are, of course, 1 astronomical unit away from our star. But there's other stars. We're kind of, if you look at there's a map of stars. It's kind of a classification system. And so it's a graph of stars that we have understood and detected and classified. And the sun is really awesome because it sits right in the middle of the graph, of course. We have the analog. But the sun is unique in that it is what we call, we'll get into that part later. It's right in the middle. It's a medium-sized star. It burns with a medium type of intensity. It's of medium type size and mass. So it's right in the middle. But you can have these really, really big stars too, super giants like Betelgeuse. Or you can have white dwarfs that are really, really, really small. So depending on the star type, depends on where that habitable zone is. Now, if you go back to that Drake equation and talk a bit about that, and when we started talking about the circumstellar habitable zone, Goldilocks zone, in the 1950s, we believed that, you know, we were the only place that water could be based on our distance from the star and atmospheric pressure and all that. Now we've come to know in the last 20 or so years that the second part of this sentence, a few other characteristics can change this circumstellar habitable zone a little bit. And that's because we have found water, not just on Earth, but we know that there is water on Europa, Enceladus, moons of planets in our own solar system. I think I even heard that we believe that when New Horizons flew by Pluto earlier, or last summer, that they believe that there could be a liquid water ocean underneath the surface as well. So liquid water is now starting to exist in places that we didn't know it could exist before. So that's pretty amazing. So that definitely changes the Drake equation. It changes our view of what a circumstellar habitable zone could be. So it gives us two new designations for this. It gives us a probable zone and a conservative zone. So probable zones would include places like Europa and Enceladus in our solar system. And the conservative would be, yes, we definitely know something like Earth could be this far away from a star, have liquid water, atmospheric pressure. So that's kind of making that Drake equation not work out as well as it once did. So it was proposed in 1953, and we'll talk about this in a little bit. But and it's being challenged nowadays, and that's exactly what I just talked about, that places like Enceladus and Europa and possibly even Pluto have water, subsurface water. So that's pretty amazing. So currently, we know of 13 planets in the conservative zone as of today, and there are 27, I guess it's called the optimal zone. So that would include the conservative zone plus other things that could have subsurface oceans or are a little further out, a little closer in. And so here's a graphic that talks a little bit about the zones. And so there we are right in the middle. There's our sun in the X1. And there's Earth in the blue habitable zone. Okay, and now we know that there could be stuff out here in Jupiter and Saturn with Europa and Enceladus moons. So when we talk about that a exoplanet could be closer or farther and still be in its own habitable zone, that's because we have things like the star size, mass, heat, etc. If it's 2 times, then it's basically the distance would be the square root of 2, 4 times square root of 4, etc. So depending on the star size, the habitable zone basically gets moved out. And likewise, if the star is smaller or dimmer, it moves inwards. So you can see on this one that says it's only 0.25 times the size of our own sun. That would only be at a half an astronomical unit. So it's basically like half of our distance to the sun. So those planets move in or out. And we're going to see this especially about when we talk about the Centauri Proxima b being. It's very, very close to its host star, but that's because it's very dim. Okay, and then here's an example of a system, Gliese 581. And you see at our top here is our sun. And you can see that the star in this system is quite a bit smaller than our own sun. Looks like it's probably, based on this graph, half or maybe a third. And so you can see at the top here, Earth is in its habitable zone in the blue area. That's where we want to be. And then we can see the planets that we've detected in the Gliese 581 system. We've detected 1, 2, 3, 4, 5, 6 different planets. And we designate exoplanets with a letter. You may notice that there's no A here, and that's because A is the star. So Gliese 581a is the star. Oops, let me go back here. B would be the next planet discovered. C, D, E, F, and G. So as we can see in this diagram, G is definitely in that conservative zone right in the middle. So that's a great place to be. It's possible this meets all of our criteria to be able to have water under atmospheric pressure at the right distance from its star. Okay, C and D are right on those fringes. So it's possible, but we don't know exactly. So we're taking guesses. B, E, and F are definitely not in the habitable zone based on their distance from their star. So that is what we're talking about. And what's interesting to note as well is G is right in the middle of its habitable zone. But if you look, it's 0.1 AUs from its star. So it's really close. So it's like kind of like Mercury in our solar system. Of course, Mercury is so close to our sun, it can never support life. But in this instance, because of the star type and size, it's very possible that could work. Okay, so that's a little bit about habitable zones. Let me check the chat and see if we got any questions. No, we are good to go. All right, so we are going to move on and talk about the history of exoplanets. So we're going to start way back when, in the 1500s. So there was an Italian philosopher, Giordano Bruno, and when he looked up into the night sky, you have to remember, in the 1500s, it was widely believed that the Earth was the center of the universe, and that the sun raced across the sky, and that the Earth was flat. Okay, so pretty amazing. And what he said is he looked up into the sky and said, all these fixed stars in the sky, they could be like our own sun. Okay, this was a new philosophy that was pretty crazy for its time. Those things we're seeing up there are like our own sun. And so he's the first person that posed this question. I'm not sure how well that went over, but very good. So fast forward to the 1700s and Isaac Newton. And Isaac Newton was one of the first people to say that we didn't orbit. Things don't orbit around us. We orbit around them. The stars, our planet orbits around the sun. Of course, the moon orbits around us. But that those other planets that we're noticing, based on their motion, also orbit around the sun. So, but he said that if the fixed stars are the center of the similar systems, just like our own, they will all be constructed according to a similar design and subject. So if those stars are just like us, then they will have the same design as our own solar system. They will have planets orbiting around their stars. So probably didn't go over too well at that time because things like that weren't widely believed in. Yeah. Okay. Fast forward to 1952. A gentleman named Otto Struve, a Russian American, came to America from Russia in the 50s, and he was an astronomer. And he was the first to talk about how planets beyond our own solar system could be closer or further from the host stars, depending on their star size. This is what we just talked about, the Goldilocks zone, the Circumstellar habitable zone. He was the first person to think about this and put out that theory. So that's a pretty big thing. And now we know, well, this is something that we've come to take and use as a way to try and understand if planets could be habitable. So pretty big. And this was only, 60 years ago, 65 years ago. And he also said that we could use methods like spectroscopy and transit methods, and we're going to talk about that in a second, that those methods could be used to detect planets. So little did Otto Struve know he was right in two different ideas that he had here. So that's pretty big. Okay, so we're going to start talking about autostrouve and how we begin detecting these planets. So the most popular method of discovering exoplanets is something called radial velocity. When people think about the methods that we'd use to discover an exoplanet, a lot of times people will think we could just take a picture. And that'd be one of the more common ways that people think about. Can't we just take pictures and count the number of planets around each star? Okay. Well, there's a lot of stars. There's some other problems with that I'll talk about in a minute. The second most popular would be, can't we just detect when a planet goes in front of a star and measure its dimness, and all of a sudden we can know that there's an exoplanet there? Yes, and we're going to talk about that in a second. But the most popular method that we've used to date to begin discovering planets was radial velocity. So let's talk about what radial velocity is. Okay, this is going to get a little wordy, but I'm going to try and make it nice and simple. So radial velocity is also known as Doppler spectroscopy or star wobble. And you might have heard that term star wobble before. It was the most popular until 2014, and we'll talk about why that is in a few minutes. And it's really great for finding exoplanets close by, but complicated for multi-planet system. And we'll talk about this in a second. So it definitely helps with larger planets. So what we're going to see is that a star is very massive, has a lot of gravity. So it's constantly pulling planets towards it. Planets are in orbits that are able to pull equally gravity-wise outwards. So that's why they don't fall towards the sun, towards their star. But what we're finding, or what we found, why this method exists in the whole first place, is because planets also have gravity. And the greater their gravity, they're doing the same thing to their star that the star is doing to them. So the planet is actually pulling the star a little bit each direction. So of course this does get complicated when you have the multi-planet systems because you have multiple wobbles in different directions. But okay, let's talk about this in some pictures. So we have this picture on the right. We've got a host star up here on the right-hand side. And we have an exoplanet going by here in the right-hand side. So now this planet is exerting some kind of force. The planet is exerting some kind of force that pulls the star towards it. Now, when we look at the star, we can notice that it's in different positions. And that wobble, based on where this exoplanet is in its orbit, shows that there is a exoplanet orbiting because the star is moving back and forth, or forwards and backwards, depending on our view of it. Now, we use Doppler spectroscopy to do this. So let's break this down, make it nice and simple. So the Doppler method is something that you might have heard of, and we talk about it on the Earth a lot, dealing with sound waves. So it'd be like a car horn going by or a train. The noise changes depending on how it's approaching you, when it's next to you, and when it's past you. And the reason that is because the sound wave distance is further or closer. So same idea here, but we're now dealing with light waves instead of sound waves. Okay, so what we do is we take a spectrogram of the star, and that's what we can see down here. And we can see, based on these little lines that are kind of hanging down on the spectrogram, this tells us what the star's composition is made up of. But But what we see is we see these lines move around, and that's because if the star is coming towards us a little bit because of the wobble, that means probably that exoplanet's lying around in here, those light waves get shorter, and as it kind of goes away from us, the waves get longer. So it's making, that's how we detect if that star is wobbling back and forth. And here's an example. I'm hoping this little animation is coming through. It's definitely an exaggerated view, but it kind of gives you an idea of what a planet is doing to its star to be able to detect this. And so this method is really, really good because for large planets, because those large planets, they have a lot of mass. They do exert a lot of force on their planet or on their sun, making them wobble like that. And this is the method that brought us hot Jupiter as well. One of the first planets detected by this method. Okay, so that's radial velocity. So we can talk about it as star wobble if it's easier to remember. Okay. Transit method and others. Okay, so I told you we were going to talk about the transit method. And so here it is, transit photometry. This is when an exoplanet crosses in front of a star. So what's going to happen is a star is going to dim slightly when it goes in front of its host star. The exoplanet will make the star dim. And we can detect that little variation. So the star only dims 1 to 2%. So not enough probably for your eyes to detect it. Because if you remember, we're looking at these stars from a great distance. And the planets are very small. And we're very small compared to our own sun. So dimming 1 to 2%. So we have to use scientific instruments to be able to use this method. There's no other way. It also helps with determining the size of the planets, because how much the star dims lets us know how big those planets are. Now, the issue with this method is that we have to be lined up just right with the star and the plane of the orbits of these planets with their host star. So as we have been able to determine, only less than 0.5% are aligned to our field of view looking at those stars to be able to use this method. So though this method sounds like it's really awesome, and it is actually how we've detected most exoplanets, the line of sight on this is really, really bad, 0.47%. So that's why we don't use this method. Yeah, I'll just leave it there. The great thing about this method is, though, that we can observe a whole lot of them at the same time, because we can just look at the sky, look at all the stars in the sky, and let the software basically look at all these stars, see which ones are dimming tonight, and use a wide field of view to do that. It is a little prone to false positives. Other things can happen, things going in front of the viewing apparatus. Asteroids, even terrestrial things here on Earth can make those stars dim. The atmosphere can make those stars dim a little bit. And that's why, the stars twinkle, is because of the upper atmospheric winds. So that's why this method is a little trickier, and we did get over some of that, and we'll talk about that in a minute. So we can also use a spectrograph like we're using in the other method, the star wobble method, when a planet is transiting, to determine its atmosphere, so that the light of that star, we know that the light signature of that star, and we subtract that from the light that comes through the very edge of that planet. And we can now detect the atmospheric. So we can see if there's an atmosphere, for one, but then we can also detect the composition of that atmosphere based on the lines that come through on the spectrograph. And then on the back side, when the planet is nearing, going behind its host star, the secondary eclipse, we can also figure out a little bit about radiation and temperature through some other methods. Okay, so that's a little bit about transit photometry. Now, timing variation is another kind that we use. It's the same as transit photometry, but we use radio waves, and specifically in pulsars, because pulsars are the timekeepers of our universe. They are stars that basically are emitting radiation in a regular cycle, pulsing on and off, which is why they're called pulsars. And then there's a couple of others. There's gravitational microlensing, which we've kind of used to determine. We've seen it most recently in being able to detect star systems behind other massive objects in the universe that bend gravity and light waves to be able to allow us to look at things behind other objects, which is really cool. Something Einstein predicted. Direct imaging, which we just talked about a little bit, and I'm going to add a picture here in a second. And there's a couple of other ones. They go down in usage as we talk about them. So here is a picture of transit photometry. So we're looking at a star, and we have all these data points of the star's brightness, right? And then we come along, and all of a sudden the star dips down, and it gets down to this low point, and then it comes back up to its regular brightness again. Okay? This is an example of an exoplanet transiting in front of its star. And when we were talking about being able to determine the atmosphere, or how that would be kind of this, either this downward slide or this upward slide. And we can determine the size of the planet by how long that this break is right here. So that's how we're able to determine some of those things. Let me show you another picture. Okay, this is actual real data. The first one was real data, but this one's way more interesting, I think. So the red dots here are the actual data points, and the black lines going up and down are the possible ranges for those data points. And so if we graph these, what we see is we see this wave happening. Okay. And that's the star wobble. So we're using the transit photometry, and we're using the star wobble methods here. And we're seeing that this, and that these are, if you notice, this wave is on a downward cycle. So if we go back, looking at the radial velocity, that means that planet is coming towards us. Okay, so pretty cool. And this data, and we'll talk about this in a little bit, is from Proxima Centauri b. So very cool. All right, direct imaging. We did talk about this a little bit earlier. And why can't we just take a picture? So here is an example of a exoplanet star system where we're able to take a picture. Now, the reason why this is a difficult method to use is because, number one, you have to block out the star. Okay, that's not the hard part. The hard part is usually that these planets are so dim that it's really hard to find them. Now, this example, we do have two very massive planets near this star. So these are probably hot Jupiters. We've got a little planet out here. Hard to say. You know, I'm not sure what the size of the star is or what this star system is, but you know, it kind of just looks like these other blobs that are sitting out here. I'm not sure what those are, but a very hard method to use. We've detected a couple planets this way. We've been able to verify a few star systems this way as well. So direct imaging. not as useful as we had hoped, just taking pictures of stars. Plus, there's a lot of stars out there. We don't want to try and take a picture this zoomed in of every star. It would take so long. And there could be stars without planets, and it would just be a waste of time. Again, this method also, we have to be at the right angle, because if we look at this, we're looking basically down on this system. We can see that there's orbits that probably go in this direction here. Okay, so if we were more in line plane-wise with it, we'd have to use, we'd be more beneficial to use the transit method. Okay. So now we move forward to the recent history of exoplanets. So in January 9th, 1992, this is not that long ago. What is that? That's 25 years ago. Radio astronomers announced in Nature magazine, a very popular place to publish scientific findings, not just of space, but of things from nature, that there were 2 exoplanets orbiting a pulsar. This was the first place that something was published with scientific evidence. And they say in their abstract that the precise timing measurements of pulses from the recently discovered pulsar, here's all the designations of that pulsar, are used to demonstrate that rather than being associated with a stellar object, the pulsar is orbited by 2 or more planet-sized bodies. So they found, using that radio spectroscopy, they found that the radio waves emitted by this pulsar were diminishing. These 6.2 millisecond pulses weren't happening on schedule. And they determined that it happened more than once. So they were able to verify that there was 2 or more planet-sized bodies. Okay, move forward a little bit further into 1995. We had the first detection of an exoplanet around a main sequence star. That's a star just like our own sun, using radial velocity. So that's that star wobble method again, right? So this was big because it was the first time that we were able to see that star wobbling. This was just theorized. And we finally discovered it in 1995. So this, it gave the first evidence of an exoplanet around a main sequence star, which was big because it means there's a planet that's orbiting a star like ours. It orbited very close and was massive. And this is where the term hot Jupiter was first used. So not even that long ago, this wasn't even a term until 1995. Okay, so now we said we're able to do this, but we would like to have an instrument that was specifically designed to do these things. And so the HARPS program was designed. And in 2003, it came online in Chile. And if you know much about astronomy in Chile, it's one of the best places on our planet to do astronomy. It's at a very high altitude. It's got very stable atmosphere. It's just like the right setup to do studies like this. And there's many telescopes down there in the Chilean Andes. So HARPS stands for the High Accuracy Radial Velocity Planet Searcher. So, of course, we just talked about what radial velocity means. That's the star wobble method. High accuracies, because we're building an instrument that's just going to be for this, solely for finding planets. And of course, it's a planet searcher, so it's kind of a silly name. Like I said, it's the first devoted instrument used to detect exoplanets, and it uses a highly sensitive spectrograph and radial velocity. It has discovered 130 exoplanets to date, which is quite a few. So this was the big hitter in 2003 when it came to exoplanet discovery. And you can see on the left picture here is what it looks like inside the machine. When they close it up, these capsules close up and the spectrogram is inside this really small area, really dark, and they shoot a beam from a star right in here, and it casts it goes through a prism, of course, and casts a certain spectrum of light, just like we're seeing here. So you can see these little lines that are detected. Okay, and then it's of course graphing this for us a little better up there, so we can determine what's going on here. So HARPS, really big, really popular, 2003. 130 exoplanets, really big. So we got to this point of saying, well, that's cool, but wouldn't it be great if we could detect planets without having to worry about the atmosphere, right? So the Kepler Space Telescope was designed for that exact purpose. There's a couple of objectives that this went to sought out to do, and it was launched in I think it was April of 2009. The Kepler Space Telescope is launched in space and comes online, and the main reason it was built was we wanted to now detect Earth-sized exoplanets. Now, we were really good at HARPS, at detecting things like hot Jupiters, but our search is really to detect something that's like us, because we know that we are in the habitable zone and life can exist here. So we want to make sure, we want to have Earth-sized exoplanets orbiting the main sequence star, which is like our sun. So up until now, it was kind of we were just kind of shooting HARPS at different objects. We weren't just targeting main sequence stars like our own. So we wanted to make sure that we could do main sequence stars. And we wanted to do it in a very wide field. So we wanted to be able to look at 145,000 stars at one time. And this is how we found out that percentage, the 0.47% of stars have exoplanets in our own plane of view to be able to use this method. So that's why a wide field became very important, because 145,000 stars at a time. One of the other main goals was to determine how many stars have exoplanets. We didn't know coming into 2009 how many stars out there actually had exoplanets orbiting them. And of course, as I told you in our introduction, that we now know that most stars have at least one exoplanet. So that's pretty amazing. We want to use photometry to detect. So that's that method that we talked about before, the transit method. And we want to, and then, so in August 6, 2009, so we launched in April, up to August we were testing. August 6th, we finally verified a previously discovered exoplanet, something that was probably from HARPS. So this proved that the Kepler Space Telescope was able to predict exoplanets. So that's pretty good. And it had a great ability to determine candidate planets. So remember, we talked a little bit about how there's other things that can come between the instrument and the star that may also factor into that being a false positive. So Kepler's been awesome in being able to say, I think this star has an exoplanet, but we need to verify that in some other method to determine that. So it's chugging along until 2013. We had a bunch of maneuvering parts failed on Kepler. The gyroscopes had some big issues, and that's what we used to be able to maneuver Kepler around in space. to be able to point at certain objects and hold its position while it's taking all these pictures. So that was really, really bad. But astronomers and scientists are very good at figuring out alternative methods of making things work. And they're able to revive the Kepler Space Telescope to continue working in a different way, but they got it up and working again, which led to the February 26, 2014 report that came out that Kepler had discovered 715 new exoplanets around 305 stars. So of course, if you can do some simple math, you can see that that means that there's at least one, and usually two, at least, and possibly three, exoplanets around those stars. So this was the first huge release of, look, we found a whole bunch of stars, or a whole bunch of exoplanets. But it's based on a new method, verification by multiplicity. So this is interpolation by saying we've been able to verify from Kepler's candidate exoplanet transits, we've been able to verify that this many exoplanets are really there that it detected. So in extrapolating those numbers of candidates, it was able to say that it found 715 new exoplanets around 305 stars. Not all verified, but it's a new method that we're using called verification by multiplicity. And we actually saw this in our own news about, I want to say 2 or 3 months ago, kind of the beginning of 2017, the end of 2016. There was a news report about how we now believe that there's 10 times, I think it was 10 times as many galaxies in the universe as we had previously thought. And that was verification by multiplicity using the Hubble Space Telescope, using the Deep Field Sky Survey to say, based on this amount of area in the sky that we're looking at, there's this many galaxies. And so if we extrapolate that across the entire sky, we now believe that there's 10 times more than we previously thought. So it is a scientific method that astronomers use a lot to be able to get numbers. In July 23rd, 2015, we discovered Kepler 452b, and this was the first Earth-sized exoplanet that was confirmed to exist in the habitable zone around a main sequence star. It's just like us. It was really huge news. You might not remember it, but this was only less than 2 years ago we found something that is our size in the habitable zone around a star like our own. Really, really big news. In May 10th, 2016, less than a year ago, another new release, 1,284 new planets were verified, 550 of which were rocky planets, and 9 of those were in the habitable zone. Huge. This is just a year less than a year later. We go from finding 1 to finding 9 more. And we're able to determine their composition as rocky planets, 550 of those. So as you can tell, based on the number we gave at the beginning, 3,000, and I can't remember the number exactly, Kepler has found a majority of the planets, exoplanets, that we've discovered. So pretty big news. Here's what the Kepler spacecraft looks like, in case you're wondering. So it's, of course, up in space. It's got its primary mirror in the back, so it's kind of like a regular telescope that most of the telescopes are these days. So the light comes in, bounces off this back mirror, and comes up onto these focal plane detectors. So the way that Kepler does this is very much like what you have in your camera phone. Any digital camera you might have has a computer chip in it called a CCD, a charge coupled device. And depending on the size of that CCD, you get a certain amount of resolution, you get a certain size of photograph. So what they've done is they've packed this thing full of 42 large size CCDs, which gives them 100 degrees field of view, which is huge. And of course, it's basically just a tube, and it's covered with solar panels, and it's got a cover, so pretty simple. So if we look inside of it, here on the top right is a picture of the CCDs. It's huge. I mean, these are big CCDs. There's 42 of them on this big plane. And I actually read this morning about why this is curved. There's a certain principle that you have that deals with the curvature of what we see in the universe, and so it was compensating by having these curved, so it ends up giving us a flat field of view. And what a picture from Kepler looks like is this bottom right picture. This is what all those CCDs look like when it comes in, and what the processors start looking at the dimness compared to whenever the last survey was done. I'm not sure how often they do the survey here. Could be every 24 hours, could be monthly, I'm not sure. They're looking at all these stars. Remember we said that there's, I think, what, 147,000, 157,000 or something stars in this field of view. And Kepler is only looking, if we look on this left-hand panel, Kepler has only been looking at this one place, just on the right side of Cygnus, the swan. And it's just looking at this one little area of the sky. Okay, and we said that it's found thousands of planets in this little bitty region with these detectors. So, and you know, there's of course like some spaces in between here, so there's probably some more stars. And you know, this is just a very small area of the sky. And we found that many. And we'll talk about that in a few minutes. Okay. To our big discussion of this topic. On August 24th, 2016, Proxima Centauri b was announced. ESO published in, of course, the Journal of Nature again in July. So just before August, they published their paper. And Proxima Centauri, the star, Proxima Centauri A, is called the pale red dot. And here is their title page: a terrestrial planet candidate in a temperate orbit around Proxima Centauri. Very simple, but has a lot of punch to it. Terrestrial, temperate orbit, Proxima Centauri. So the closest star to Earth in a good orbit around a terrestrial planet. Lots of people, of course, were involved in that paper. You can see by the names. And here's their abstract. And what's interesting about this abstract is, you know, it has some math in it, but it has some very interesting things. So it's telling us that the red dwarf Proxima Centauri star is 1.295 parsecs away, approximately 4 light years. It's the sun's closest stellar neighbor, low mass star. So it talks a little bit about its temperature, how bright it is, how big it is, 12% the mass of the sun. It's a moderately active star, how much it rotates, and that it's basically comparable to the sun. The new observations reveal the presence of a small planet orbiting Proxima with a minimum mass of 1.3 Earth masses, so it's about the size of Earth, and has an orbital period around its star of approximately 11.2 days. That's pretty exact, I think. And with an equilibrium temperature in the range where water can be liquid on its surface. So by the time that this was announced to the public on August 24th, 2016, the media went crazy. The New York Times, one star over, a planet that might be another Earth. The Telegraph, Proxima b, alien life could exist on second Earth, found orbiting our nearest star in the Alpha Centauri system. So a lot of speculation made in the media. These are just two. I tried to take two of some of the biggest newspapers in the world that talked about this. Proxima Centauri being the closest star to our own. A lot of people think it's Alpha Centauri. Alpha Centauri and Beta Centauri are also very close, but Proxima Centauri is just a little bit closer. So people said, oh my gosh, it's the second Earth, because they said it's the same size and it could have, and their excerpt says where water could be liquid on its surface. It doesn't say it is liquid on its surface. So the news went crazy with this. So let's look at some of the facts about Proxima Centauri b. It was discovered by the radial velocity method, which is that star wobble. Not the transit method, but the star wobble method. The size of it is 1.3 times the mass of the Earth, so pretty dang close to the size of the Earth. We currently do not know what its composition is. We know that it orbits its host star, Proxima Centauri, every 11.2 days, approximately, which is a very fast orbit. It does live in the habitable zone where water could exist, and that's because the star is a lot smaller. So that's why its orbit is very close too. It's only 4.22 light years away. And this is one of the reasons people kind of went crazy over this. It's very close by. That's not far at all. 4 years away if you could travel the speed of light. And this is the actual diagram that they used for the radial velocity method. This is the actual data that determined that this exoplanet was here. So there you go, and it's moving towards us, I think we said earlier. So if we dig a little bit deeper, we find out that Proxima Centauri is a volatile red dwarf star. Well, that's not good. It's volatile, right? So harboring life sounds pretty unlikely. Proxima Centauri is 12% as massive as our sun, so it's a lot smaller. And that means that Proxima Centauri b has to be a lot closer to its star than we currently are. Which is also how we know that it orbits in 11.2 days. It's got high gravity because of that as well. Proxima Centauri, the star, had a very active life early on. Lots of radiation, so life as we know it probably couldn't exist. Because of all that radiation, the atmosphere probably got blown away. If it did have water, it probably escaped into space, was vaporized. But I've seen some papers that discuss how life could exist here, life that we do not understand quite yet, if it was able to evolve to the radiation. Though it lives in the habitable zone, the proximity to its host star and the history of that star leads to believe any water that might have existed there was evaporated long ago. We just said that. And any life that we would know and understand is probably unlikely. And I see, this is less than a year ago now that this came out. I still see an occasional paper come out about how people believe that, oh no, well, we didn't think about this possibility, that life could exist if it did this or it did that. So it's still up there. So what's the intrigue? The intrigue is how close it is. We can imagine being there because it is so close, only 4.22 light years away. That's really close in the grand scheme of the universe. And there's a program called the Breakthrough Starshot, and I think Stephen Hawking is part of this program as well. But it's a program where they want to send approximately 1,000 mini probes, these little bitty things. You can see the picture there on the right, at 20 to 30% of the speed of light off to Proxima Centauri B, at least Proxima Centauri. It'll take 20 to 30 years to arrive going that speed, and then 4 to transmit back the data, because they're not coming back. They just transmit the data in those radio waves, move at the speed of light. So it takes 4.22 years to arrive back at Earth. And the probes are of a couple different designs, I believe. Take photographs, take certain scientific readings. And the reason that we have about 1,000 of those is there is safety in numbers. If we know a lot about space travel, we know that you have to be prepared for the inevitable. And that means that we need to take into account things that we don't know that might happen along the way. So lots of redundancy built in by having approximately 1,000 of those guys, flying off to, and with that many, they may be colliding into each other. So that's the reason for that. But definitely check out Breakthrough Starshot. It's really interesting. I think since I gave this presentation originally, I think the program has moved ahead a little bit more even. So that is pretty cool. Okay. So something new since the presentation that I gave last fall is TRAPPIST-1 system has obtained a little bit more data. It was discovered in 2015 that there were 3 exoplanets in TRAPPIST-1. And then in February, about 1 month ago, 4 additional exoplanets were announced in the system, 3 of which were in the habitable zone. The reason this became big news, not because the 3 in the habitable zone, although that did up our number that we know in the habitable zone, but it was the most planets, a total of 7, that we saw in a single system that we were able to detect. And if you see in the graphic there on the top, those are your 7 planets in the TRAPPIST-1 system. You can see B is orbiting its sun in 1.51 days. That's really crazy fast, and it's really, really close to its sun too. And even way out there in H, you're talking about only 20 days orbit, and it's only at 0.06 astronomical units. So really interesting. And I want to say that E, F, and G are your habitable zone planets. It might be D, E, and F. I can't remember. Yeah, TRAPPIST-1. So it was in the news lately, so I did want to cover that off. 7 planets in one, orbiting 1 star. So pretty amazing. Okay, wrapping up, we want to talk about what we've seen out there. So we are in the Orion spur of the Milky Way galaxy, denoted by the cross hatch there with the sun. And if we look at Kepler and where it's looking, remember we showed you that little spot that it was looking at, and it's always just looking at that one spot so that it can keep looking and seeing if there's changes. So it's looking off in this little cone here, and it's looking about 3,000 light years away. Okay, this is all Kepler's looked at, and it's found thousands of planets, right? Approximately 3,500 in this little bitty area right here. Not nearby, pretty far away. There's still all this Milky Way, right? So if we look out a little further, this is not a picture of the Milky Way. There is no picture of the Milky Way, but it is like our the design of our galaxy, a spiral galaxy. So here we go, out a little further. We're looking in this direction here. Down this a little bit. Look at all this other area we haven't even surveyed. We haven't looked out into. So remember, approximately 11 billion possible Earth-sized habitable planets in our own galaxy. We've already found quite a few. I mean, we found what was the number 9? I think in the conservative zone, just in this little bitty bit. Okay. Now, if we extrapolate out even further, and we said that there's, I can't remember the number now that they're giving for the number of galaxies in our universe, but you take these numbers and you extrapolate them out, and you say, wow, there's approximately 11 billion possible Earth-sized habitable planets in our galaxy, and now you multiply that times the number of other galaxies out there. Now I ask you that question again that we posed at the very beginning. Do you think it's possible that there is intelligent life on other planets in our universe? If there's 11 billion in our own galaxy, possibilities. Or is Earth just that strange rare occurrence that happened to have the right elements and happened to have something happen that made life happen here? Okay, I want to wrap up with a thank you and a picture of the Centauris. You got your two bright Centauris here, Alpha Centauri and Beta Centauri. The little red circle is Proxima Centauri. Notice you can't even see it. It's so small. This is where that Kepler, or where that Proxima Centauri b exoplanet, the closest planet near us outside of our solar system, is orbiting. So that should give you, and of course looking at this, remember we said almost every single star out there probably has a planet orbiting it. Pretty crazy. So with that, I want to say thank you, and yeah, look for us on other broadcasts. We'll be doing some other live broadcasts. I want to do some more of these live ones. And check out our Facebook page, facebook.com/Thalamer Observatory. We're going to be doing some more local events very, very soon. And let us know how you liked it. I think with that, I'm going to stop the broadcast. And I thank you for coming and listening in to our presentation today. Thank you. Bye.